This morning?
Pretty good.
So you got your test tomorrow, huh? Did you put in your 7 hours in the library on this stuff?
Yeah.
Do you feel good about it?
Mostly.
Okay.
There's a couple problems I have no idea.
Okay. Let's have a look at them.
18.
Okay. What's the first thing we should do to try to sketch A?
To be honest, I have no idea where to even start on this problem.
Okay. Well, always factor. So, in other words, if you don't know what to do, we'll factor the numerator. We'll factor the denominator. Now, let's lay out a grid. What you end up with, whenever you start with a rational quotient, the first thing you want to do is lay down your asymptotes. You want to lay down your vertical asymptotes and your horizontal asymptotes, and that's your new grid. So, how about vertical asymptotes? First thing.
Would it be x, or would it be 2 and negative 2?
Just whatever makes the denominator 0. It's always your vertical asymptote. That's easy. Horizontal asymptote.
I'm completely blanking.
When the power of the variable, when the degree of the variable in the numerator is the same as the degree of the variable in the denominator, then the horizontal asymptote comes at the ratio of their coefficients. In other words, 1/2.
Okay.
So there's our grid. Okay. Now, we know, I don't want to draw it on there because it'll be too hard to erase, but you know what a hyperbolic function looks like, right?
Yeah.
Okay. Well, this is a hyperbolic nature. In other words, it's going to look like a hyperbola in the upper right quadrant. It's going to look like a hyperbola in the lower left quadrant. And then it's going to do something in between your vertical asymptotes. So one thing that would be nice to know is, does it cross the x-axis?
Okay.
I'm going to go ahead and draw a good guess. Now what it does in between, it can do this, or it can do this. Okay, that's usually the possibilities. Now I may be in the wrong quadrants. Instead of being in the upper right-hand quadrant, that hyperbola may be in the lower right. In other words, I would, but I can answer all of those questions. First thing I have to answer, is there a place where y is equal to 0? Or f of x? Because that'll tell me if it crosses the x-axis. If I can't find any place that y is equal to 0, well then it doesn't cross the x-axis. How about in this case here? Let me try to erase. In other words, to determine whether it's the red or the blue, it's really going to be based on whether it crosses the x-axis. So if I set this equal to 0, can you solve it? Is there any answer where that is true? If it is, then it crosses the x-axis. What makes a quotient equal to 0? Only if the numerator is equal to 0.
So
What makes the numerator 0?
1.
1 and minus 1.
Okay, so plus minus.
So there's an intercept. There's an intercept. Well, that tells us that it's not the blue line. So let's erase that, because it's got to go through the x-axis. Now, what kind of line might go through that x-axis? Both spots. Now, another thing worth knowing is, am I in the right quadrant? In other words, let's ignore in between the vertical asymptotes for a moment. We have figured out that it goes through these 2 points, and it doesn't go through that point. Now let's figure out if it crosses the horizontal asymptote.
Okay.
In other words, that horizontal asymptote is y equals 1/2. So the question is can I solve this problem?
Would you just plug 1/2 in
For the y, for f of x.
Yeah.
And if the function is ever equal to 1/2, that means it crosses that horizontal asymptote also. Well, does this have a solution? The 2's eliminate, and I can say this, x minus 1 times x plus 1, can that possibly be equal to x minus 2 times x plus 2? Does that have a solution?
No.
Well, let's try to solve it. That's x squared minus 1. That's x squared minus 4. You're right. That does not have a solution. Minus 1 is not equal to minus 4. Therefore, it does not cross that horizontal asymptote. Now, you can never cross vertical asymptotes. That's just the rule of math. Okay? But you can sometimes cross horizontal asymptotes, but obviously not here, because I can't get above that horizontal asymptote without crossing it. So now I have a pretty good idea what it probably does in the middle, because it doesn't go up to that, so it must do something like this. Remember, against vertical asymptotes, it can only do one thing, head towards infinity in one direction or not. Okay, so I think I got the middle right. Now the question is that in the right spot, or should it be down here? How do I answer that?
Can't you just plug in a number less than -2 and a number greater than +2?
Perfect, do it. Start on the right. Let's go right to left. for some reason it works better on these if you go right to left. So plug in plus 3. What's the numerator become?
The numerator becomes 8.
What's the denominator become?
10.
Okay, that's above 1/2, right?
Yeah.
Okay, so this one is correct. Now, let's just check the other one. Plug in minus 3. What do you get? I think I still get 8 in the numerator.
Yeah.
And in the denominator, I got minus 5 times a minus 1. I still get 8/10. So, am I in the right quadrant with that lower left?
No.
No, I got to move it. And that makes sense because usually they always, when you cross a vertical asymptote, I'm not going to say this 100% of the time, but I'll bet almost 100% of the time you get the problem. So there's our curve. Okay? Now here's what I'm saying. If I come from the right, this thing's going up to infinity. On the other side of that vertical asymptote, I would expect to come up from negative infinity. Opposite way. In the middle, when I get to this point, I'm going down to negative infinity. On the other side of the vertical asymptote, I would expect to come down from positive infinity. Okay? And that's pretty much how you're going to do all of these. You're going to figure out your vertical asymptotes, your horizontal asymptotes. You got to know the rules for both of those. And then you got to figure out whether there are any x-intercepts and whether it crosses the horizontal asymptote. And make sure that your curves are in the right quadrants. Once you do all of that, the curve kind of draws itself. Okay. Now, should we do 18b?
Yeah, we can.
Vertical asymptote. Is there anything x cannot be?
The square root of 3.
No. That denominator can never be negative. Never can be 0. X squared is always positive, and when you add 3 to it, it's always positive. So there are none.
Okay.
Horizontal asymptotes.
0.
No. Remember, the powers are the same.
Oh, wait, yeah, so it'd be 1.
All right, now. Let me think for a moment how we're going to do this. Is there an x-intercept? Remember, x-intercepts are where y is equal to 0. In other words, solve that.
No.
What?
No.
Remember that for a quotient to be equal to 0, the only thing that has to be true is the numerator has to be 0.
Oh, okay.
So we do have an x-intercept at 0 right there. Does it cross that asymptote? Is this possible? For all of that to be equal to 1, which would mean x squared would have to be equal to that. Again, you get 0 equals 3. No, it does not cross that horizontal asymptote. Never gets on the other side of it. And it only crosses the x-axis in one spot. Now, how are we going to draw this? Well, I know the function goes through this point. Is the function ever negative? Can that ever be a negative number?
No.
Okay, so the whole function has to be drawn between the horizontal asymptote and the x-axis. I'm guessing something like that. We know the end behavior is going to approach that horizontal asymptote as we go to plus infinity and minus infinity. So the curve almost has to look like that. This was a much easier problem. Just to show you.
So if I have to do this on my test, would I just plug in a couple numbers just to show her that that works? Or how do you think I should?
Yeah, let's first of all make sure that we've got it right. You can't use a calculator in this at all, can you?
No, we can use the calculator.
Oh, you can.
Yeah.
You use a graphing calculator?
Yep.
Well, how do they keep you from just using a graphing calculator like I'm using right now?
Because we have to show, we have to show work.
Oh. So now I understand your question more. Okay. And notice that that is how it looks. It looks a little more exaggerated because they've made the horizontal asymptote way up here. But that's basically how we do it. Now, you make a very good question. What work would you have to show here? I guess the best work you could show would be this. If you have to do a problem like this, this is the way you want your answer to look. And this is all you need to do. Vertical asymptote, none. Horizontal asymptote, y equal 1. X-intercepts, in other words, you're going to go through exactly the procedure that I just went through.
Okay.
Horizontal asymptote intercepts, none. So, what else could it be? Oh, f of x, or g of x, excuse me, always greater than or equal to 0. So write down those 5 things, and that can only result in one curve. It goes through only one x-intercept, never goes negative, never touches the line y equal 1. Well, what else could it be other than this? You could, if you're worried about it, plug in a few points. You know, x equal 2, then y equals 4/7. In other words, start creating 1 or 2 points. I wouldn't overdo it. In fact, 1 point, x equal plus or minus 2, y equals 4/7. So we know it's also an even function. In other words, you could say that g of negative x equals g of x. That's what even functions do. And an even function means it's symmetrical about the y-axis. So the only point you'd really have to plug in is one or two values of a positive x. State that it's an even function, symmetrical about the y-axis. However it looks to the right, it's going to look to the left.
Okay.
Okay. This is actually would be a better way of doing it than even using your graphing calculator. I mean, it's nice to check your work, but this is the way you do all of these, is these steps right there. First of all, you try to lay down your grid. And our grid, in this case, is only that area right in there. That's the only place we can draw our function.
Okay.
All right, what else we got?
Let me look. Let me look real quick.
Oh, we got a lot of them.
Can we do?
Wow, they go all the way to 31. Do you know how to do all of these objects of rotation?
Where does that start?
29, I think.
Yeah, can we do? Can we start at 29?
30. In other words, 29 is an area problem. When you have area problems, they're pretty easy. Okay.
Or it's just to identify the error. I don't really know where the error is.
Okay, let's do 29. Let's do 29. We'll still have time to do 30. I want to do at least one of these solids of rotation, because those can be tricky. Okay. Well, there's the error right. No. So the derivative is what? Or what's the antiderivative of cosine?
Sine.
Okay, so that's correct. And we're going to take the sine evaluated at the top number minus the sine evaluated at the bottom number. Well, that's true. But let me make sure I'm okay. So there's pi.
Oh, okay. So
that's 0. That's the correct answer. It's a negative sign. And then the sign of minus pi over 2 would also be negative 1. So that's correct. Two negatives becomes a positive. One appears to be right. I'm not sure I see an error.
What it's asking is not for the net area, but the total area. So I think she wants it from negative pi to 0 to 0 to pi.
This area here is negative area. So the way you solve that problem is you take the absolute value of the function. If you take the integral of the absolute value of the function, you will get the total area. You won't get the net area. Okay? Now, we could accomplish the same thing by doing this in two steps. First of all, let's draw the right curve. It's not the sine curve we want. It's the cosine curve. and this is pi. Okay? So we can see immediately that the total area I could do it in 2 steps. I could figure out the area of that, which is going from minus pi over 2 to pi over 2. Okay, that'll give me an answer. It's all positive. And then instead of subtracting, I'm going to add the area from pi over 2 to pi. Because normally this would be a negative quantity, but the error in the calculation here is that should be a positive one if we're looking for total area.
Okay.
And this is a fine way to do it. That's almost easier than doing the absolute value, unless you're doing it on a calculator. In other words, I can do this on a calculator and say, put the absolute value of cosine of x in there. And then that would give me my answer, which is going to be 1. Or not 1, more than 1. Whatever this comes out to be. Should we do this or not?
No, I got it. I didn't
What you got to
realize.
do is draw the curve of the function, not the antiderivative. You want to draw the curve of the function, and then notice that this is all positive area. This is all positive area. So I can just do it from minus pi over 2 to plus pi over 2, and I'll get all that area. Okay? And then I got to do it from pi over 2 to pi to get this area. And that's going to be a negative number, but I got to add that to that.
Okay.
Okay. Yeah, a little tricky. Okay. What next?
Just one of
how about
30?
Let's do 30. These are probably as tricky as they get in calculus. I mean, in terms of when you first learn calculus, this is a tough part to get. You have to really understand three-dimensional geometry, kinda. All right. So do you know how to do these at all?
Yeah, I just not completely.
Okay. Let me ask some questions. They've taught you how to break it up into disks, correctly? Correct?
Yes.
They've taught you how to break it up into washers, correct?
Yeah.
And they probably have not taught you cylindrical shells. Yes, they have. I'm seeing that in 31. Okay. So those are 3 things. Disks are pretty easy. If we look at this function, y equals square root of x. Okay. And I'm rotating it. I'm also got y equal x in there and the x-axis. I'm rotating the whole thing about the x-axis. So when I get done, I'm going to have a solid that looks like a tulip. Now let's see, where is y? You know what? I didn't draw this correct. Let me draw this better. And it matters. If your drawing isn't correct, you're not really looking at the right figure. Here's my y equal x. where does that intersect with y equals square root of x when x is 1?
Yeah.
So those two curves intersect right there, and up until then, it's like that.
Yeah.
So in other words, this curve is above this curve between 0 and 1. So now when I rotate it, I get a solid that looks a bit like a flower, where all of this is empty space. But I end up with a three-dimensional object that looks kind of like that. So what am I going to use, discs or washers?
Washer.
Correct, because there's a hole. If there's no hole, you use a disc. But if I were to try to, and boy, there's one thing I've always wanted in calculus that I would give anything for, although not so much online, it wouldn't be that helpful, but in person it would be. And that is a box full of discs, a box full of washers, and a box full of cylindrical shells. And what you would discover is that you can make any of these shapes. I can make that shape with a box of washers. Because all I need is a lot of different ones that have different radiuses, both inside and out. So what I have to picture is that I have built this three-dimensional object using washers.
Okay.
Now, a washer is like that. Okay, it's got an inside radius and an outside radius. We're going to call it capital R and little r.
Yep.
Well, if I'm going to add up all of these washers, then am I integrating along the x-axis or the y-axis? And the answer is
Y.
the x. It's the skinny side of the washer, and it's perpendicular to the x-axis. In other words, I suck as an artist, so I'm not going to be able to draw this, but I'm going to have a washer kind of there. And then I'm going to have a washer there. Can you see that the skinny side of the washer is perpendicular to the x-axis?
Yeah.
So I'm going to add up the volume of each washer. Well, what is the volume of a washer?
Isn't it like pi?
It's the area of the outside, pi r squared.
Yeah. Minus the area of the inside.
Yeah, that's the area of the hole. And that's the area of the washer. So if I want the volume of the washer, I got to multiply it by the thickness of each washer, and that is dx. In other words, it's dx that's going to approach 0. And then I'm going to add all these up. So in reality, this is a true statement. Every washer has a dV that is pi capital R squared minus pi little r squared times dx. Okay? So if I want to solve this problem, I integrate both sides. And now when I integrate dV, I get V. When I integrate the right side, I can pull out the pi. It's a constant. And I'm left with r squared minus little r squared dx. Or, yeah, dx. What are my limits of integration?
I don't know.
Well, I'm going to go from this point right here to that point right there, because that's where that solid ends. It goes up to 1. So I'm going to
So
integrate
0 to
from
1.
0 to 1. In other words, let's assume that I had 10 washers that fit in there pretty nicely. Then I would just add up the volume of all 10 washers, and that would be the volume of my solid. Now, if I had 100 washers, it would be closer. It's a little bit like rectangular approximation method. The more rectangles you put in there, the more accurate you get. Same thing with volumes. And that's why dx is the skinny side of the washer. It's the one that's going towards 0, giving me literally an infinite number of washers in there. In which case I will have the exact answer. Okay, so let's solve this integral. Here, let me erase some stuff here. I'm going to solve it in this color. I like this color better. So the volume equals pi times the integral from 0 to 1. What's capital R squared?
Square root of x squared.
Squared, which makes it just x.
X.
Minus, what's little r squared?
X squared.
Correct. And all of that is the dx. And now that's a pretty easy problem there. Do you have a need to go through that?
No.
Okay. And in this case, there's no positive volume or negative volume. You are literally adding up the volume of every washer. So the washer has a certain volume. It doesn't matter if part of it's below the x-axis or not. In other words, every one of these blue washers that I drew has a volume. It doesn't matter where it's at.
Okay.
Okay. All right. Let's go on. Now, if I had a problem like this, where it says just rotate that from 0 to 1. In other words, if I had only y equals square root of x, then what would I use?
Disk.
Okay, give me the volume of this. To the integral, and I want the volume if I rotate from 0 to 1 again. So I'm going to rotate this whole thing. So there's not going to be a hole when I get done. And I can use disks. You only need to use washers if there's a hole. I suppose one could say you could use washers 100% of the time, and when there's no hole, you make your little r 0. Okay. Now, what is going to be the volume of each disk? It's pi r squared times dx, right?
Yeah.
In other words, the volume of each disk is the surface area, which is pi r squared. R squared in this case is x, and the skinny side of each disk is perpendicular to the horizontal axis, so I'm going to integrate horizontally. There are lots of problems where you can integrate vertically, and then instead of doing a dx, you're going to do a dy. When you look at cylindrical shells, you need to figure out the skinny side of that cylindrical shell and what is it perpendicular to? Is it perpendicular to the x-axis or the y-axis? Now, okay, so you know the difference between disks and washers.
Can we do 30C? Because that one doesn't make sense to me.
Okay.
Just how it's written.
Sure. And the hardest one's going to be these cylindrical shells, but let's do that.
Yeah.
Okay, so we're going about the y-axis here. I believe that's y equal x to the fourth approximately. And y equals 0 is the x-axis. X equal 1, we'll call this point right there. And the y-axis. So they're saying take this part of the curve, rotate it about the y-axis. Well, you end up with something, a solid three-dimensional, call it a ashtray. Can you picture it?
Yeah.
What am I going to use to here? Remember, I'm rotating it this way.
Would x to the fourth be big R and then?
First of all, let's figure out if we're going to use discs or washers.
It would be washer.
Yeah, because these little spots right here, that's going to create a hole in your ashtray. So you can't build this ashtray using discs. You need washers. And each washer is going to be like that, basically. And the skinny side of that washer is perpendicular to the y-axis. So our integral is remember, it's pi times r squared minus little r squared times dy. What does that tell us? That tells us that these functions that I'm going to integrate have to be functions of y. They can't be x. They got to be a function of y. Well, if I look at this curve and I want to know what that measurement is, it's x equals the fourth root of y, is it not?
Yep.
Okay. It's the outside radius.
Would it just
That's
be
the inside radius.
okay? So it'd be x equals 1.
Exactly. The outside radius is 1. So it's 1 squared minus y to the 1/4 squared, which is y to the 1/2. And I'm doing it between 0 and 1. Actually, I'm going to do it from -1 to 1, which is the same as 2 times 0 to 1. Because it's an even function, it's symmetrical, so whatever I get, you know what? I don't even want to do that. Let's just do it right, from -1 to 1. Now, the very first washer that gets laid down is this outside one, which has a radius of 1. And it has an inside radius of y to the 1/4. In other words, this measurement is the inside radius, correct? Actually, let's put the inside radius in blue and the outside radius in red. So I believe I've drawn my picture correctly. And that's relatively straightforward to do also.
Okay.
Okay. Now, whether you'd get exactly the same answer if you went from 0 to 1 and then multiplied that by 2, I suspect you would. But I'm not sure you want to do that. We're talking volumes here. Yeah, we don't want to get into symmetry of volume. So let's just do it properly. We're going to integrate from -1 to 1. And we're going to integrate a y function, not an x function. All right, shall we look at cylindrical shells?
Yeah.
You got a piece of paper like a dollar bill on you?
No.
You got any kind of rectangular piece of paper?
Yeah.
Take it, fold it so that it makes a cylinder. That's what a cylindrical shell is.
Okay.
Okay. Now, these are tough to explain. The best explanation I know of has to do with a bundt cake. Hold on a second. I want to make sure I get the drawing right. Before we tackle these problems, I got to be able to explain it to you. And it's not that easy to explain. I hate these indexes where here we go. 387. Here's the perfect problem to explain cylindrical shells. Let's say you took this rotated it not about the y-axis, but around the line x equal -1. Okay?
Okay.
What you end up with is kind of called a bundt cake. Okay? There's an empty space. What you have is a round cake with a hole in the middle of it. Okay? Now, notice that I could do this using washers, using flat washers that were perpendicular, whose skinny side was perpendicular to the y-axis. Okay, you can see how you can do it that way, right?
Yep.
The other way to do it is with a cylindrical shell. In other words, if you take your outside piece of, you got to have a certain amount of artistic skill here. The cylindrical shell is going, the skinny side of it is going to be perpendicular to the x-axis. And that's the biggest difference between using cylindrical shells as opposed to using washers. If I use washers, I have to integrate it on the y-axis. if I use cylindrical shells, I'm going to integrate it on the x-axis because the skinny part of the cylindrical shell is perpendicular to the x-axis.
Okay.
Okay, so that's kind of the concept of cylindrical shells, is you can take a lot of these objects that you could build with discs or washers, but you could also build them with cylindrical shells. In other words, imagine a dollar bill wrapped into a cylindrical shell that you could vary the radius of the shell or the height of the shell. In other words, if you kind of look at a water tower. I think I got the curvature on. Okay. A water tower that's empty of water. So the sides of the water tower are the sides, the skinny side of your dollar bill that you folded.
Okay.
Okay. And all right, let's just do the one they want us to do here. I'm going to graph that on Wolfram Alpha momentarily just so I don't waste time and we can maybe finish the problem. 4x squared minus, what was it?
4x minus
4x minus x squared, okay. 4x minus x squared. Oops.
Yeah, you messed up.
Minus x to the 62. Wow. That's a funny looking graph. That's interesting. If you don't put in it, it assumes it. All right. So there's the curve. We are going to rotate that about the y-axis, I believe. Yeah. And the other line is y equal x. Oh, man. Again, it gives us something that looks like, well, here, let's just do it like this. Y equal x. These are equal at 2. Okay? So I'm going to take this area right here. I'm going to rotate it about the y-axis. So ends up giving me a solid that looks something like that. Now, I'm going to integrate from that point to that point. In other words, the very first dollar bill I laid down to create this thing let's examine these cylinders. Because I've got to add up the volume of all my dollar bills. Okay, let me just draw a dollar bill here. Okay, there's a dollar bill. If I turn that into a cylinder, then I need to know the height of the cylinder. Boy, hold on a second. It's been a while since I've done cylindrical shells. let's see, what is the volume of each shell? It would be the surface area of that dollar bill, which is the width, which happens to be pi r squared, times the height of the dollar bill.
Okay.
Times the thickness of the dollar bill, which is dx. So I have h pi r squared, which is this measurement right here, times dx. Now, what is h in our picture?
H. Would H just be y equals x? So x?
No, the function that's above is the x squared, I believe.
Okay.
Yeah.
Yeah.
In the picture. Yeah, because when x is equal to like a quarter, then you're taking 1 minus a 16th, so you would be above the line y equal x. So the height is 4x minus x squared. Oh, no. Well, hold on. I know how to do these, but in 4 minutes, I can't figure out how to do it. I'm sorry, because I know your test is tomorrow, but I've got to review. Here, let me see if I can do a quick review here. Cylindrical shells. All right. It's just been too long since I've done a cylindrical shell problem. It's probably been 2 years. In Calc AB, you don't do cylindrical shells. You just do discs and washers. So it's only when you get beyond Calc AB that anybody has to do cylindrical shells. I'm going to have to put you off on this one until next time. Hopefully they won't ask too many questions on it.
Yeah, probably not.
Trying to think here. The height is definitely the area of that rectangle is the height, which is 4x minus x squared, times the base, which is pi r squared. But what is r squared? R squared is the measurement between there and there. What is that? That is, if y equals, this is tough because you cannot solve it for y. Therein is the key. Here, let me minimize that a little bit. In other words, every now, I'm glad this came up because every now and then you we are integrating about the y-axis, right?
Yeah.
That means that means we're rotating about the y-axis. But because we're using cylindrical shells, the thickness of each cylinder is perpendicular to the x-axis. So we're integrating along the x-axis. And we are going to integrate from, what does it go from? 2? No. 4? Yeah.
No, it's
4.
2. Oh, yeah.
Well, let's see. When x is 4, y is 0. So I think I want to go from -4 to 4. In my picture, where they crossed was at x equal 4.
No, they crossed at x equals 2. At least according to the Wolfram Alpha one.
Well, y isn't equal to 0 when x equals 2. Oh, it's where the y's are equal. In other words, it's where x is equal to 4x minus x squared. And that's not at 2 either. In other words, if I solve this, 4x minus x squared has to equal x. Well, that means 3x has to equal 0. How did Wolfram Alpha get 2 on this? It didn't. It goes to 4. In other words, the two zeros are 0 and 4.
Oh, okay.
Okay. Now, when we integrate it, notice that we're rotating this about the y-axis. So we do kind of end up with a bundt cake. In other words, we end up with something that looks like this, if I can draw it real quickly. And it's a cake. In other words, it's round. Okay? And I could do it using washers going vertically, but notice the problem. If I try to integrate that vertically on the y-axis, I've got to have a function of y, and I don't. Here's my function. Well, try solving that for x. You can't do it. In other words, I can't give it a convenient function of y because I can't solve that. Therefore, I'm going to use cylindrical shells because I need my function to be a function of x, because I'm going to integrate it on the x-axis. So I'm going to integrate it from -4 to 4. The height is merely that function.
Okay.
The distance, the volume of each cylindrical share is the height times pi r squared. R is the distance between those 2 points. In other words, at this point in time, I got a cylindrical shell. One side is there, the other side is there. Okay? So that distance is x. That's r squared is x squared. dx. There you go. That should give you the right answer. Now, that's fairly easy to integrate because you can multiply the x squared and then just do it piecemeal. But see if that doesn't give you the right answer. I'm almost positive that's the correct thing.
Okay,
When you get your
I'll work
limits,
on
the
it.
limits of integration are a little confusing here because the outside is at -4. For the very first cylinder on the outside goes from -4 to +4. All right, Mitch, I'll let you go. I know I've run over here a little bit,
Okay.
but that's definitely, I'm 95% sure that's correct for this
Okay.
problem.
One thing, where is the recording for this?
Okay,
Because I know you used to put it on YouTube,
I do.
but okay.
And
Is it
more importantly is I can get it loaded up there almost immediately. There's no processing required anymore.
okay?
Let me send you a link right now. Hold on, I'll send it to you by way of GoToMeeting. I got to figure out where it is. It is right here. I know where it is. Right here. I'm going to paste it into the chat window.
Okay.
Go ahead and click on that and see if you don't get what I get. I clicked on it also.
Yeah, I got it.
Okay. And then you're looking for the files that start out with MH is
Yeah,
your file name.
yeah, I see it.
Okay, good.
All right.
Mitch, I'll let you go. Good luck on your test.
All right. Thank you.